The last class we have been discussing about this differential amplifier. So during this discussion, we always consider that the diff amp was said to be a linear symmetric circuit, right? So this is what we are considered, and based on this, we try to evaluate few parameters. So one was VOD by VID, which is nothing but, what is this definition of VOD by VID? The differential gain, right? Yeah. So for this differential gain, what was the result that we got? Yeah, it is minus GM of the input device into RD, and if you want, you can just put R0 in parallel with it. Okay, so this is what we have discussed, and also we also evaluated something known as common mode output for the common mode input, VOCM divided by VICM. So again, this is nothing but our common mode gain, and that also could be defined as something like minus RD, assuming that the lambda is equal to 0. I can just write it as something like this, right? And if at all, if I have a tail node that is having a resistance of RSS, then I can write this gain expression to be something like this. And apart from these two combinations of VOCM and VICM and VOD and VID, we also had other combinations, right? So one of the combination was VOD by VICM. The other one was VOCM divided by VID. So what happens to these quantities? They were zeros. So why is that? So in the first case, what happens is that whenever I have a symmetrical input, what happens to the output nodes? They will also be symmetric. And when we try to measure them differentially, they tend to cancel each other, due to which the output goes to 0, right? So whereas in this case, I am trying to feed in an antisymmetric input. So which means that I would get an output that is again antisymmetric. And when I try to combine those antisymmetrical inputs, the antisymmetrical outputs, they tend to cancel each other again, okay? And also there is one more important property that we discussed when we had this antisymmetrical input. Apart from this output nodes being antisymmetric, there is one more important property that we always tend to have in our packet. What is that? What happens to the common node? The node that connects to different symmetrical circuits? Yeah, that goes to an AC ground. Okay, so those are the two important properties that I need to consider when I go for antisymmetrical inputs. Okay, so I guess you would have also seen the notes. Okay, so based on that, I will just try to discuss few other things. What happens the moment? Okay, let me write it as observations. So what happens the moment the RSS is being replaced with an ideal tail current source or tail current sink circuit? The RSS becomes infinity, and due to which among those four factors gets modified? Yeah, so because of this, the ACM goes to 0. Okay, so this is the first observation. There is also one more observation that I want to recollect, just because I haven't thought here, but I've given as a notes. So what happens if I have some sort of non-idealities into my circuit? Say for example, I have RD1 which is equal to RD, and if I have RD2 which is not exactly equal to RD, but there is some sort of variation of delta RD along with it. So this is one of the case. The notes also had discussed what happens if this GM1 is not equal to GM2. Now when I have those non-ideal behaviors in the circuit, what happens to these terms that I have? Something gets modified here. Which is that? Yeah, obviously this AD is, yeah, so even this could get modified, but those expressions are already defined, okay? So just because these quantities are pretty much small, they won't modify our AD or ACM much far away, okay? So what happens when I have these non-ideal conditions? Because this delta RD or delta GM that is going to get introduced will generally not affect this differential gain or the common mode gain. Not much. It's a very tiny bit of change that will happen. What else can happen when I have these non-idealities into my circuit? I think the notes had discussed about all of these things. Yeah, so the third and the fourth term would then become a non-zero factors. Okay, so previously we had a zero factor here for both of these conditions. The moment I introduce this non-idealities, what happens is that these terms will never be a zero. They will have a finite amount of quantity along with it. Okay, so these are the observations that we have. You should have got it from the notes or from the lecture. Okay. So now, in order to refresh ourselves till what we have done, what we do is like just quickly do some small exercise, and then we'll jump into completely a new topic, and then we'll get back to our differential amplifier again. Okay, so this particular example is just a refresher of what we have done till now. Okay. For this given circuit, how would we analyze the circuit and get the differential gain out of the circuit? Yeah, so first of all, is the circuit is symmetric? That is the very first phenomena that we need to consider here. Is this circuit is symmetric? So can we draw a line of symmetry for the circuit? Yes. Okay, so when I try to draw the line of symmetry, it exactly comes here, right? So I have one part which is an exact replica of the other one. Right? So this particular portion is exactly replication of the other part. So due to which the circuit is symmetric, and now since we are asking about a differential gain, the type of input that I am going to feed is going to be a antisymmetrical input. So what happens to this node when I apply this antisymmetrical input? Yeah, this node would be driven to the ground. So I will have this M1 and M2 source terminals getting connected to the ground whenever I apply antisymmetrical inputs. So now that I have this particular circuit, and it is enough for us to take only one part of the circuit to analyze the entire gain, right? So for this circuit, the type of resulting circuit that I would get would be something like this. Yeah, there is one more question for you guys. What happens to this node? Yeah, so we said that this particular node is common. So we just plug that particular node to the ground. So, but what about these nodes? Yes. Okay. So even this node is actually connecting both the circuits. If I see this part of the circuit is actually making a connection with the other part of my circuit. Basically, this node acts as a kind of common bridge between both the circuits. So this also will be driven to ground. Clear? So because of that, I have some sort of picture like this. Okay, where I have one end R. And this also goes to the ground. I have one more circuit where I apply my Vin. So right now this Vin1 would be entirely replaced with VID itself. Okay, and here is where I'm tapping my output, which is labeled as VOD. Okay, now for this circuit, what is the gain? Okay, so if I look down, what I have is this RO1, 2, but when I look up, yeah, so I have this RO3, 4 that goes in parallel with resistance R. Okay, so this completes my R out. But what about this capital GM? What is the capital GM of the circuit? When I short this particular V out to the ground, it would be minus GM1, 2. That's it. So you found the gain. Okay. So obviously the next topic that we are going to discuss is something related to a differential amplifier with active loads. Okay. Now in order to discuss about this differential amplifier with active load, first of all, I have to discuss about the active loads, and in order to create the active load, we also have to talk about something known as current mirror circuit. So now in order to discuss about this particular topic, I'm just going to deviate myself into something known as a current mirror circuit. Okay, just to talk about this particular circuit. Okay, because that helps us in the analysis that we are going to discuss in the case of a differential amplifier. Okay, so let me begin with this topic of current mirrors. You already know the basic current mirror. But before that, let me just try to understand why we exactly need of this current mirror. Okay, so I'm just going to take all the circuits that we have done till now, which had a requirement of this current mirror. Okay, now in both the circuit, what type of load we have connected? Which one is my load and which is my input device? Yeah, in both the cases, my M2 is an input device and M1 would act as my load circuit, right? And the one that I have towards the left is nothing but, what type of configuration is this? It's a common source. What about this? Common drain. Okay. Now in each of these cases, we know that this M1 is actually mimicking what is known as a current sinking circuit, right? Both these M1s are basically mimicking a kind of current source or current sinking circuit in this particular configuration. Now, the whole point is that we know that when a particular device or a mass is being operated in a saturation regime, then I can ensure that this could be replaced with some sort of current sinking or current sourcing circuit. So in this case, whatever I have as an M1 acts as a kind of current sinking circuit, and in order to have that kind of current sinking capability, I need to make sure that this M1 is being operated in the saturation regime, okay, for which I have to ensure that I need to provide some proper value for the VB. Okay, are you clear? I need a current sinking circuit, and in order to have a current sinking capability into my MOS transistor, I have to ensure that both these M1s are being operated in my saturation regime, and I need a potential VB which is larger than the value of VDH, right? Now the question is, how do I generate this VBs? How do I generate this biasing potential VB? Yeah, so there are different ways by which I can generate this potential of VB. Okay, I'll just go ahead with one that we will not practically use it, and later we'll just come up with some sort of result which we will quite often use in our circuits. Clear? So I need a value of VB. I could generate the value of VB by having some sort of resistive biasing scheme. Okay, so whatever the scheme that I have here, in order to generate the value of VB, is known as simple resistive biasing. Okay, now I also want to define the value of current that flows through this M1 transistor as I out. So one could approximate the value of this I out to be equal to, assuming that this transistor is in saturation regime, how will I express this I out? Yeah, so I have to write down this current equation of half Kn dash W by L. Yeah, so I will have something like a voltage divider for generating the VGS, right? So this voltage divider is nothing but, yeah, VDD into R2 by R1 plus R2 minus VDH the whole square. Okay. When I look for this expression of this I out, there are certain dependencies I could see here. Okay, the very first dependency is that my I out depends on VDD. The second one is on the process parameters like Kn dash. So when I look for the quantity that defines my I out, I could see that the voltage VDH is basically varies between the wafer itself. Okay, so say for example, I have a silicon wafer that has some sort of threshold voltage. Okay, now if I, in the same wafer, if I look at a different transistor, the threshold voltage of that particular transistor would be different from what you have chosen from. Clear? So the value of VT is not constant throughout the wafer itself. Okay, and that is one thing that bothers me. So it varies by like almost like 100 millivolt from wafer to wafer, and also this VDH exhibits the temperature dependency. Okay, so whenever there is a rise in the temperature in the ambience, the VDH also varies. So again, that is something that we never want to happen. Okay, it is not only this VDH that depends on the temperature, but what about this mu? The mobility of these electrons will also depend on the temperature. So you could able to see all the parameters that I have to define my I out in this case is actually cannot define the proper value of I out. Okay, yeah. So if I look for this I out, the I out depends on these variables, and these variables in short depends on the temperature and depends on VDH, which varies with wafer to wafer. So everything is kind of buggy here. So and there is something that we have to bother is that we always want to have this VOV around this load to be minimum or larger. How do we want this VOV for a load to be least, right? Because whenever there is a swing, I want to make sure that the VOV of this load supposed to be as small as possible. So now that when I try to bring down this VOV, what happens is that, as I said, the threshold variations are quite high in my device. Okay, if I move from one transistor to a different transistor, the threshold varies a lot. So due to which, say for example, if I could able to approximate the value of VOV of a single transistor to around 100 millivolt, then when I just move this particular transistor from a given wafer, say for example I have picked a spot to define my M1, I also have picked one more spot which is quite away from this M1 transistor in the single wafer. This will have a different VDH than compared to this one. But I assume that both the value of VOVs for both the transistors are of 200 millivolt. But when I really see, they will not be having the same value of VOV across this VDS. Okay, just because the threshold voltage of this device that I have here is completely different from the threshold voltage that I have for one more device that I have in the silicon wafer. Okay, so you would find somewhere around 100 millivolt variations within the same wafer. And when I compare this 50 millivolt, when I compare this 50 millivolt to a 100 millivolt requirement, what happens is that this creates almost like 44% of error in defining the output current. So that is a kind of buggy that I have when I go for this simple resistive scheme. Again, all these resistors are all bulkier. We cannot use it in an IC. Clear? And apart from that, the resistors also have more sensitive to the temperature, and it induces much more noise in our circuit. Okay. So because of all of these factors, we want to identify a circuit that defines the requirement of this VGS. Okay. So let us look for a circuit that helps us to define the proper value of VGS for this load, okay, which is nothing but the VB potential. Now anything that you can think about it, I need a VB to be defined for the load, and how will I generate that VB? So basically let us assume that there is some sort of reference current is there in my circuit. Okay, so it exists in my IC. Okay, I assume that this I reference is existing in my circuit. I will talk about this I reference again when we talk about BGR, band gap reference circuits. But as of now, we'll assume that I have an ideal reference current, and then through this reference current, I just want to mimic some sort of current sources in my circuit as a load, and some sort of current sinking circuit as a load for devices. Is that clear? So from this ideal reference circuit, I want to generate these loads into my system. Now, how do I generate these copies of this I reference, like I1 here and I2 here? How do I do this process of copying? Yeah, I need a current mirror. Okay, so as I said, we are not worried about this, how this I reference has been generated, but I assume that there is an I reference in my circuit, and through this I reference, I'm just going to create copies of those I references as I1, I2. So in this case, I1 is nothing but a current sourcing or sinking circuit. It's a current sourcing because it is being connected to the VDD towards the some sort of node. Okay, whereas the bottom one has a current source which is connected directly to the tail or to the ground, whereas the other end of my node is connected to some different nodes. Okay, so this is my current sourcing circuit, and whereas this one is nothing but the current sinking circuit. Okay, so just by using this reference current, I could make a copies of these I1s and I2s into my circuit. In order to have those copies, I have to talk about the current equation of my MOSFET, okay? Because it is being connected to the VDD and it is sourcing to the circuit at the bottom, right? So say for example, if I have a CS amplifier, this would act as a load. We are worried about only the load. For the entire discussion, I am talking only about the load, okay? So this is my CS amplifier with NMOS as my input device, okay? So here is my Vin and here is my Vout, okay? For this circuit, I should have the same CS amplifier which I have just shown at the previous slide. So this is my I2, where I am feeding my input here and taking my Vout here, okay? So this is how I use my I1 and I2 in the circuits, okay? So for each of these circuits, I want this I1 and I2 to be a copies of this I reference, and we are looking for this copying circuit. Now in order to generate this copying circuit, I have to understand the mass current equation first. So we know that when the transistor has been biased in the saturation regime, the current equation that flows in the MOSFET could be expressed as a function of VGS. Am I right? It's basically a function of VGS, right? The current that flows. Yeah. But what we wanted is a VGS out of it. I don't want the current, but what I rather wanted is the value of VB or the VGS to these loads, right? To these loads, what is really required is the value of VB or VGS. So what I can do is that I can just perform something known as an inverse function, okay? So if I do so, I need an inverse function that acts on the value of ID such that it generates me back the value of VGS. Now, what type of circuit can do this kind of operation? Generating this relation is pretty easy. Just apply a particular value of VGS to a MOS transistor, and that in turn defines the current through the device. Okay, so I could do this first part, but how will I generate the second part? I need the second part to be generated. I need a VGS for a given current. Yeah, so I can go for a diode connected. So let us try to fix that and see how a diode connected configuration can generate the value of VGS out of the circuit. So let me take an I reference, okay, and then I am passing this I reference through some sort of transistor, but this transistor is actually being diode connected, okay. Now when I try to force a current through this particular transistor, say for example M1, what happens to the value of VGS here? Yeah, the VGS would be automatically set by the current that is flowing through this drain, okay. So this in turn generates the appropriate value of VGS for the device. So this particular circuit helps me to extract the value of VGS for a given current, okay. Now that I have got this VGS and I want this value of VGS to apply to these loads such that I generate the value of I2 out of the device, right? So what I do is that I got the value of VGS, which is nothing but the value of VB, that I connected to a transistor, and in turn it defines the current for me ID. Are you clear with it? Yeah. I hope that this entire process you might be already familiar with it. So the only thing is that I'm just trying to brush up. So let me try to define this I out. Now I out is basically a function of VGS that is defined, right? So I just write it as it's a function of VGS, and this VGS was in turn defined through the current by applying an inverse relation here. Am I right? Yeah. So this VGS has been plugged with F inverse of the I reference, okay. So when I try to remove all those functions of F with F prime or F inverse, what happens is that I would end up having a result which I would write it directly. I know how to get these results, but I'll just write down the end result of it. Okay, so when you apply F multiplied with an inverse function of it, you end up having a result which results in a factor of W by L of 2 divided by W by L of 1. Okay, so these are nothing but the normalizing factors here. Clear? So I will not talk much about it because you know all of these results well before. So I'm just trying to recollect it. Okay. Any doubt in this? Shall we perform a simple exercise? So let me have a circuit. Yeah. So express this I out in terms of I reference. You guys got it? So how will I define this I out in terms of I reference? First of all, I need to know what is the relation that is shared from this point to this point, right? So the current that is flowing through this drain of M2 to the drain of M1. So what is that relation that they share? L of 2 divided by W by L of 1. And then what is the relation that they share between the drain of M3 to drain of M4? Okay, W by L of 4 divided by W by L of 3. Any doubt in this? Okay, are you clear? Yeah. So, or alpha times that of beta. So these are a kind of short form that I'm using it. Yeah. So calculate the voltage gain for the given circuit. Small signal voltage gain. Shall I talk about the answer? Yeah. So now, the whole point is that whenever there is a small signal over here, there is a small signal current that flows. And the value of this current is basically Gm1 times that of Vin. And this Gm times that of Vin, when it flows, it creates a small signal sort of VGS around this M2. This VGS is what has been copied here, the small signal VGS, and it tries to generate my ID3. Now, what is the relation that I have between this ID1 and ID3 is the question. If you know that, then we can just try to write the expression of this V out as ID3 times that of RL. Now, what is that ID3? Yeah, so we know that the current that is flowing through this device, I can write it as Gm3 times that of VGS. I can do that. But the current that flows through this device, how will I define this Gm basically? I need a DC quantity, which is nothing but it is proportional to capital ID that is flowing. Now, if the ratios are different for both the device, then the current that is flowing through this particular path is different from the current that is flowing through this particular path. Okay? So let us assume that I have this capital ID2 that flows through this. So whenever I try to compute the value of Gm1, I use this capital ID2 or capital ID1 in order to compute that. But whenever I go for Gm3 computation, I have to use the capital ID3. Now what is the relation that they share between this ID2 or ID1 with ID3, capital IDs? Yeah, they are different by the W by L factors because there is a mirroring circuit. Okay, so I could express this ID3 in terms of ID2 or ID1. So what is the relation that I would have? W by L of 3 divided by W by L of 2. It has to be 2, not 1. Okay, yeah. So anybody wants to know why it is not 2? Why it is not 1? W by L of 1? No. First of all, the transistors are all not same, right? So in this case, my M2 and M3 are same. I can compare with them. But M3 and M1 are completely different transistors. Okay. So I don't have those commonalities like to cancel out this Kn dash with Kp dash. I don't have such kind of cancellation techniques. Okay. So that's the reason. So with this taking into account, then what happens is that I can re-express this Gm3 in terms of Gm1 itself. So how I can express this Gm3 in terms of Gm1? Currents are different. I got the ratios, right? So who is defining this Gm3 is ID3. In the place of ID3, I have to fix this factor, and ID2 will define my GM1. Am I right? So that's it. Any doubt in this? So this is GM1, and there is a factor that sits, and this particular factor comes from this particular expression requirement. Okay. Now, there are different ways of writing this GM, right? So one is square root of 2 ID kn dash W by L. The other one is 2 ID by VOV and kn dash W by L VOV. Now, out of this, any of this we no need to consider. Among these first two forms, which form do I need to consider between this this branch and this branch? First form? No. We will not discuss about this third form. First let me compare only these two forms. Among those two forms, which form I need to compare between the first branch and the second branch of the circuit? Second one. Why? Yeah, VOs are same for both the device. Okay, I cannot compare with the IDs because the ID that is flowing through my M2 and M1 is not same as that of my M3. I cannot use the first form. I guess we discussed about this particular concept even in the case of a diode connected configuration, CS amplifier. Okay, so that's the reason why I cannot use the first form, but rather I can go for this particular form. In the similar reason, I can also go for this. Okay. I think I have one small exercise, but it's a pretty simple, but the question is a bit lengthy.